Dear friends, welcome back. So, in our previous lecture we have solved the takeoff performance of a delta wing UAV. So, what we did is we developed a subroutine that estimates the power requirement by this UAV to take off from a location or a runway which is located at about 1 kilometer with respect to mean sea level. Now, we know what is the power requirement during takeoff, right, and earlier we have also solved the problem for power requirement during cruise. Now, we will try to solve for the power requirement during climb condition, so that we will understand what is the typical power requirement for this aircraft to perform a particular mission, right. Apart from this cruise, if you want to loiter for some time, right. So, what will be the, apart from flying at a particular velocity for a given endurance, what will be the corresponding power required? We will see aspect, we will solve as we progress. So, for the time being we are going to solve this climb performance, what is the power requirement, so that the details about this power requirement will help us to understand. So, with these details we will be able to understand the corresponding specifications or the kind of power plant that we need to select. So, now let us take up a problem, same problem almost. So, instead of this, so example, consider the UAV in the above example, or say in our previous example, and estimate the power required by the system, not by the UAV, to perform climb at a climb rate of say 5 meters per second. Okay. So, for us this data is inadequate, isn't it? So, just before proceeding this to this particular subroutine development, we will have a quick look at the dynamics that we have discussed earlier for climb performance. Let us say this aircraft is moving at a forward velocity V infinity, right, is said to be in climb with a climb angle gamma. So, let us assume a steady climb in this case. So, where the thrust is acting in the direction of flight and drag is acting opposite to the direction of flight, and there is lift perpendicular to flight velocity, and the weight of the aircraft is acting vertically downward here, right. So, the dynamic conditions here are T minus D minus W sin gamma is 0, right, since we are considering a steady climb here. So, L minus W cos gamma is 0. So, that means the load factor N, which is L upon W, is cos gamma. Okay. So, during climbing flight I require less lift compared to that of level flight. I require to generate a lift which is adequate to overcome a component of weight, which is W cos gamma, right. So, W cos gamma will be balanced by this lift. So, W cos gamma. So, W sin gamma is balanced by the engine here. So, we are loading engine more in case of climb, right. So, W sin gamma will be acting opposite to the direction of flight. So, which we need to satisfy. That means, the thrust required by the system is drag. Apart from drag, you also have a component of weight, right, which is W sin gamma, right. Higher the value of gamma, greater is this particular component W sin gamma. So, now if this condition has to be satisfied by the engine here, right. That means, we should make this thrust available to the system to overcome the drag as well as to carry the weight, a component of weight in the direction of flight, right. So, now the power required by this system is thrust required times V infinity. So, the thrust required here for climb, I will say the bracket C talks about climb, because we also discussed TR for level flight as well. So, TR in bracket C talks about climb. So, the thrust required during climb should be, right. So, the drag plus W sin gamma. So, this is equals to drag times V infinity plus W sin gamma times V infinity. So, I need to know this particular value. If I have to solve this above example, I need to know what is the power required, or say this is the power required by the system. What should be the power available by the system? This power, shaft power that need to be generated by this engine. So, which we discussed earlier, right, is not it? So, the shaft power here that we need to generate, right. Sorry. So, this is for electrical efficiency, right. So, the shaft, otherwise the efficiency, propulsive efficiency eta P is equals to power available upon shaft power, right. So, with the help of this propeller, we are converting the available shaft power from the brushless motor or the engine, right, to the available power that helps the aircraft to move forward. So, this is power available, the output from this propeller and brushless motor combination. So, the output is power available upon shaft power is the propulsive efficiency. So, if I want to know what should be the shaft power, ultimately the engine delivers shaft power, right. So, if I need to know what is this shaft power that the engine has to deliver is equals to power available upon propulsive efficiency, right. This is what we need to ultimately figure it out. So, here the shaft power that I need to generate is equals to, so this should be the power available to move at this particular flight velocity as well as at this particular gamma, right. So, if you can notice here, so this power drag times velocity is nothing but power required in level flight, is not it? Power required in level flight. So, in level flight we just require our engine to deliver this particular power required to fly at this particular velocity. But in case of climbing flight, we apart from this power required, what we need is additional power that carries a component of weight at a desired climb velocity or forward velocity that helps you to climb, right. So, now the shaft power PSH is that the engine has to deliver or make available for the propeller or the aircraft is power available or the power required by the system upon shaft propeller efficiency, right. So, from the above step, let us say if you consider, so yeah, this as so this is like second step and this is like, so because from step 3 we will be able to find out what is a power required or the power available that need to be made available by the propeller power plant for the aircraft to fly at this particular velocity V infinity. Now, in this particular question we were given the data about rate of climb, right. The R by C stands for rate of climb, or you can also say ROC, rate of climb. So, I would like to use both the nomenclatures. So, both of these as a nomenclature to represent rate of climb, which is given as 5 meters per second. That means, the vertical component of velocity h dot is equals to V sin gamma here, right. This vertical component of velocity is V infinity sin gamma and the horizontal component of velocity is V infinity cos gamma, right. For example, so at time t is equals to 0, this say this is like t1, the time at which the climb is initiated, and then after a time t2, say t is equals to t2, so it has climbed to an altitude hf, right, let it be h2 and h1 be the initial altitude at which the climb is initiated, right. It can be 0. So, the total change in the vertical distance is h2 upon h1, right. This is h2 minus h1 upon T2 minus T1, that is h dot here, that is a vertical component of velocity. When you are climbing at particular gamma, you also cover a horizontal distance which is x dot. Say this is like at t is equals to T1, you are at x1, and at t is equals to T2, you are on the ground, you are at x2. So, this h and x are with respect to a frame that is fixed on the ground, we call it as inertial frame here. So, this is nothing but x2 minus x1 upon T2 minus T1, right. So, this is equals to V infinity cos gamma, fine. Now, say you are given the information about rate of climb r by c. So, can we directly use that rate of climb to find out what is the power required? So, one way to do that is, so from this equation, from the above equation, so this is power required for climb PRC here, right. So, now this PR stands for power required for level flight. Well, let us keep the same flavor of this PR, that is that we used it for level flight condition. So, the power available from this equation which was presented in step 3, power available minus power required will helps you to, like the difference between that power available minus power required, which is power required is drag into velocity, which is a level flight power requirement, right, is will help you to propel this aircraft forward by taking a component of weight at a velocity V infinity, right. So, this V infinity sin gamma from here is power available minus power required upon gamma upon W, called the difference between PA and PR is the excess power, and when divided by W we call it as specific excess power. So, this rate of climb h dot, so given h dot is equals to PA minus PR upon W. So, the power that need to be made available is depends upon h dot times W plus power required, right, is not it. Power required is drag into velocity. Given h dot here and you know the weight of the aircraft, if you know the drag, right, the PR, you will be able to find out what is PA. So, this PR is nothing but drag into velocity again. So, here d is again a function of CL here now, is not it. So, d is again a function of CL, and CL depends upon gamma. To find out CL, you need to know what is gamma. That means, it is not a straightforward approach, you need to consider different values of gamma and see for the same rate of climb how the power requirement is varying. Now, say you can also have a iterative approach in terms of, like instead of fixing this rate of climb at 5 meters per second, you can also iterate rate of climb for different, at each and every rate of climb you can vary the value of gamma and see what is the corresponding power required by the system, and also what will be the forward velocity that results in, right. So, we will try to figure out all these aspects. So, let us follow this step by step approach. So, approach. So, first consider a rate of climb r by c or ROC, right. For this rate of climb and vary gamma, right. So, for a particular rate of climb vary gamma. From here, for each and every gamma, for each r by c and gamma, find V infinity, which is forward velocity, right. That is what we just discussed. So, this is the forward velocity that we are talking here. So, find this forward velocity with the input of rate of climb ROC, right, rate of climb, and so this d h dot is rate of climb, right, this is ROC, okay, or r by c you can say. So, with the input of rate of climb and gamma, find out what is V infinity, forward flight velocity here in the climb, right. And then, so you know gamma and you know V infinity for this particular case, that means, so the approach that we are adopting stands for a particular r by c, right, the single value of r by c, and you can iterate the entire procedure, you can repeat the entire exercise for different rate of climb. So, r by c and gamma find V infinity, and now find CL for given V infinity and gamma, right. So, this corresponds to again for this particular rate of climb. So, once you have this CL, you find out what is, so find or say calculate CD, right, which is CD naught plus KCL square using drag polar. Okay. Once you know CD, so find the thrust required during climb, which is drag times velocity plus W sin gamma, right, sorry, drag plus W sin gamma here, right. So, now you can find out, once you have that, find power required during climb, right. So, the power required is equals to during climb, okay, should be equal to thrust required during climb times V infinity, corresponding forward velocity of flight during that climb, right. So, this you have estimated from step 5. So, which is nothing but power required for climb is power required during cruise, which is drag times velocity plus W sin gamma times V infinity. So, this anyway you will get it from this step 5. So, now you can also find out what is the time, right. You know what is the climb angle and you know what is this. You can find out what is the, say, how much time to take, time taken to climb a particular altitude, right. Otherwise, within a specified time, what is the distance it can travel, because it is a steady climb we are talking about, right. You know h1 and h2 and you know what is the h dot, you know rate of climb, and you know what is h2 minus h1 upon delta t. So, this constant velocity of climb, so which is nothing but V infinity sin gamma, you know what is V infinity and gamma, right. So, from here you will be able to find out with it. So, within a particular time interval you will be able to find out what is the height that this aircraft achieved, right. How much within, say, or say to climb a particular altitude, what should be the corresponding height, what do you call it, time required. So, that means h2 minus h1 is given, you will be able to find out what is the corresponding time. Let us consider, let us add some more to this question, time of rate of climb to climb an altitude of say. So, this is pretty much straightforward, no? There is not much much exciting thing involved with this. So, 1000 meters, okay. So, which is like how much time it takes to climb this particular altitude, okay. That is V infinity sin gamma. So, so the time taken delta t is equals to, so delta h, let us say if you are climbing from sea level to 1000 kilometers, so 1000 meters, or the problem is already, right, delta h to be 1000, say it is already starting from 1000 MSL. So, let us make it 2000 MSL here, okay, 2000 MSL. So, another important aspect that we need to consider is the drag here, right, is not it. So, the drag, you are calculating it from half rho v square s times C d, right. So, as the altitude changes here, your density also changing, is not it. So, assuming you are flying at a constant velocity throughout, you have to consider the change in density as well. So, earlier we have come up with a subroutine where with the input of altitude you will be able to find out what is the corresponding density, right. So, we will use that subroutine in this to find out drag at each and every altitude when you are flying at a particular velocity and at a forward velocity and at particular climb angle, okay. So, this is delta h upon V infinity or rate of climb, right, V infinity sin gamma, okay. Similarly, you can find out, so what will be the horizontal distance that you can travel, which is x dot is V infinity cos gamma. So, since, see, ideally it has to be a numerical integration, but we are considering a constant velocity of flight. So, we can use direct you can use delta t directly to figure out what is the corresponding distance traveled, right. So, corresponding distance travelled, horizontal distance travelled in this time, right, is V infinity cos gamma times t. So, delta x or the horizontal distance covered is V infinity cos gamma times delta t. So, delta t you get it from the previous step, step number 7, and with step 8 you will be able to find out what is the corresponding horizontal distance travelled. So, these are the parameters that we are going to plot, right, for various climb angles, right. So, we have to make a subroutine. So, this was our previous question, performance, takeoff performance subroutine, right. So, I would like to take a new code here. I am clearing the memory of this MATLAB compiler, and then I am closing, say if there are any figures or some windows which were opened because of the previous code, they all will be closed, and then CLC stands for clearing the screen of the command window. For example, if I write something here, then say CLC will actually clean this command window, clear screen, right. So, now since we are talking about the same UAV earlier, so I would like to input the geometric as well as aerodynamic data from my previous code here, right. So, I have just copied the input geometric data, right, where the mass of the UAV is 3.5 kg. So, the weight is now obtained by multiplying the mass with g, which is considered as 10 meter per second square, and the span was given as 1.5 meters with a root chord of 0.9 meters and a tip chord of 0.15 meters. So, we end up having a taper ratio of about say 0.167, and the area of this planform as per the geometry based upon this root chord, span and the tip chord with the taper ratio, you will be able to figure out what is the area which turned out to be 0.787 meter square, and the aspect ratio here is b square upon s. So, so the which is about 2.86, and Oswald's efficiency is given as an input 0.89, and W wing loading is estimated here, right. So, apart from that, so I am just explaining what are all involved here. Okay. So, now apart from that, we also considered the aerodynamic data with CL naught as 0.06, and CL alpha of this delta wing UAV is 2.992, close to 3 per radian here again, better to mention it is per radian. So, CD naught is 0.03, and induced drag correction factor can be calculated using this expression, and we also have propeller efficiency, which is 0.95, right. We require propeller efficiency, is not it. So, in order to find out what is what is shaft power that need to delivered, so we need to we need this propeller efficiency as an input here. Okay. So, now what we need to do is to consider the climb parameters, right. So, what we want to vary here, so rate of climb I would like to vary, let us say rate of climb, so r underscore c here, I would like to vary initially the rate of climb. So, that is our first step, right, for a rate of climb is equals to, so varying from say I would like to vary it from 1 meter per second to with an interval of 1 meter per second again to say what, to 7 meters per second, let us say rate of climb. So, we were asked to find out at the question was to figure out rate of climb, right, no, not rate of climb, what is the power required when you are climbing at 5 meters per second, like with a vertical velocity of 5 meters per second. But here we are not just limiting our approach for 5 meters per second, vertical velocity of 5 meters per second. Instead, we are now iterating from 1 meter per second of vertical velocity to 7 meters per second. You can increase this. I just thought like this will be useful for you when you are when you want to change these parameters. So that's the reason why I am including it here. So let us say j is the variable of this particular iteration for rate of climb, and I would like to consider another variable I for this as a variable in this integration. So not integration, I am sorry, variable for this iterations here, right. So, j is now increasing, right, whenever there is an increment in the rate of climb. So, initially it takes value of 1. So, I would like to store this ROC, rate of climb, as j comma 1. So, it is a vector, column vector here. So, rate of climb is equals to r underscore c, right. Now, so let us say for the first iteration it takes a single value of ROC, right, that is 1 here. Now, once I considered rate of climb, so according to our approach, we need to vary gamma, right, is not it, that is what it is here. So, we have to vary gamma here. So, this value has to be varied here. So, now to do that, what I am considering is another for loop, because I need to vary it, I need a loop here to vary that parameter. So, gamma is now varied from say 1 degree. So, otherwise Fp I will say I will write it as flight path, Fp is varied from 1 degree to, so it is in degrees, I will convert it into radians. So, 1 degree with an increment of otherwise say 2 degree flight path angle with an increment of 2 degrees. Every time it takes an increment of 2, say if starts with 2 degrees of gamma, then it will in the next iteration it will take 4 and 6 and so on till say 20 degrees of gamma. So, we will have almost 9 data points here, right, okay. Including 2 it is like 20, I guess, right. Including 2 it is 10 data points we will have. So, and this flight path is varying. So, again as I mentioned, I is the variable of this iterative approach for gamma, where j is the variable for ROC, rate of climb, I is for gamma here. And then I would like to convert gamma, which was there, to radians, right, because MATLAB understands radian. So, the flight path angle, which is in degrees, is converted to radians by multiplying it by pi by 180. And now, I would like to store this values of gamma as well during the iterative process. So, it is like I comma j. So, it anyway is going to be constant. So, but still I would like to store this for every k, right. So, this will be like this will be like what is the size of Fp? Size of Fp cross size of Rc. So, that will how the matrix of gamma will be, okay. Size of Fp cross size of Rc. So, I comma j. So, each and every column corresponds to a particular rate of climb here. So, that is what it is, j talks about rate of climb. So, j here x comma y in the sense here I comma j stands for each value of a particular value of rate of climb, you can say. So, this is equals to gamma. So, ideally all the columns has to be same, because it is nothing but now we have fixed our steps of increment from 2 to 20 with the interval of 2. So, ideally all the columns of this gamma capital, right, GMA. So, it has to be same, identical, it will be anyways. So, once you have gamma, find with for each r by c and gamma find v infinity, right. What will be the forward velocity of flight? We have vertical velocity of flight, which is rate of climb. Now, what will be the forward velocity of flight for this particular rate of climb? So, this equals to I comma j. So, I stands for different gamma what at for a particular. So, v of I comma j stands for different gamma, that means I is varying inside this loop, right, the second for loop, it is varying for the second for loop. So, let me close this. So, this will end the second for loop and we have the second for loop inside the first for loop, right. So, now it makes sense, right. So, this particular sub sub loop which is inside this main for loop, right. So, we will iterate for gamma. So, once we select a particular rate of climb, so this second loop iterates for gamma here. So, that is what it is. For a particular j value will not vary until you break this loop, until you break this for loop here. The gamma, until the gamma varies from 2 to 20 with a step of 2, this j value remains constant. Once it is done for the first time, it will break this particular loop, it will come out of this inner loop, and it will like again check for the condition for the outer loop here. Once there is an increment in the rate of climb here, the j value increases, and hence the new again the gamma is again varied from 0 to 2 to 20 with an interval of 2, right. Now, that those values will be stored in second column there, right. So, I wish you might have already got used to this environment and then started using MATLAB as well. So, with that what do you call assumption, I am proceeding to solve this. So, V of I comma j is equals to, we have rate of climb upon sin gamma, right. So, r underscore c upon sin of gamma, which is Ga ma here. So, gamma is already in radian. So, rate of climb is constant for a particular, but gamma is continuously changing inside the loop, and this is constant for this inner loop, to be frank. So, for our, when it comes to the outer loop, r by c again changes. When it once the inner loop starts from here, it will remain constant for that particular loop, right. Whereas gamma will be the variable of this loop here. So, we have velocity of climb and then thrust required, if I am not wrong. So, calculate what is the CL for the given, right, V and gamma, V infinity gamma. How can I do that? We have lift is equals to W cos gamma, this is what I need to produce. So, CL is equals to 2 times W upon S. So, that is wing loading times cos gamma upon rho times V infinity square. So, we have V infinity and gamma, and these details are given, geometric details, and density I need to find out at each and every altitude, right. So, when I have to find the density, that means I need to know what is the corresponding altitude of flight here. So, I need to give, for the time being, let us say we get it from here, we will try to arrange that. So, density is also given as an input. For the time being, let us assume that. Okay. So, otherwise we need to solve this entire procedure in time domain. So, let us not do that for the time being. Okay. We will consider density as an input, that is the density of the density from which the climb is initiated. So, from the density at the altitude from which the climb is initiated. So, we have that function. So, we have density function which was used earlier here. No, takeoff was not, yeah, input density, we have already used this function. So, we consider the initial altitude of cruise. So, density. So, we are confining this to the initial altitude, which can be solved in the time domain. I wish you should take it as an assignment, but just modifying the variables of the integration. So, z, let us take z as an input here, which is the enter the altitude of flight, initial altitude of flight, or altitude, enter the altitude at which cruise is initiated, at which climb is initiated, climb is in meters. So, this I am talking about performance, not takeoff. So, we will type climb, and of course, all these are meant for power plant selection. Okay. This entire exercise helps you to figure out what should be the power plant here. So, you have V, rate of climb sin gamma, and then you can find out what is a CL value here. CL of this flight is I comma j should be 2 W upon W underscore S is already like considered here, which is wing loading, the which is W by S. So, here we can't give W upon S, right. We can't use any mathematical operations to define a variable. So, W by S stands for W upon S, wing loading here. Okay. So, W underscore S times cos gamma upon density times V square, V of I comma j square. So, from here I will be able to find out what is CL, right, the corresponding CD of this flight, CD, which is CD naught given, right, CD naught is given here. Using drag polar we can find out what is CD naught is given, K we have calculated. So, CD naught plus K, these are constants, times CL is a variable again here, depends upon flight velocity and gamma, right, and gamma is a variable, and hence the flight velocity as well here, because rate of climb is again a variable in this. Okay. CD is done. Now, I will find out what is the drag. It is good to find out what is the lift as well, that is nothing but W cos gamma, that is okay. So, instead of drag I will say directly the power required, instead of drag or say thrust required, KCL, yeah, KCL square. So, the thrust required here is equals to, so thrust required for cruise, say, so climb, CL, TR underscore CL stands for climb, thrust required for climb is drag, right, which is half rho V square times S times S is given half rho V square S CD of I comma j corresponds to that particular velocity and CL. That CL of course, which depends upon V and gamma there, right, half rho V square S times CD plus W sin gamma. Okay. So, this is a thrust required W sin gamma. So, the power required or should be made available for this climb performance I comma j should be equal to thrust required for this climb performance multiplied by the corresponding velocity of the flight, forward velocity of flight. Okay. So, this is done. So, if it has to reach an altitude of say wherever it is going to take off, it has to reach an altitude of or say the cruise altitude and the takeoff altitude, the difference between them should be 1 kilometer, let us assume that. Then the time taken to reach that altitude T of I comma j which depends upon again gamma flight path angle here. So, is equals to, so let us say the difference should be 1000, we are fixing it here 1000 meters, right, multiplied upon velocity, right. So, V of I comma j. So, here the time of flight, here rate of climb is fixed, right, is not it, and we have that vertical this vertical distance is fixed and rate of climb is fixed. That means, this will not be a variable inside the loop, inside the second loop, this should be the variable in the first loop itself, right. So, that means, so here the time to climb for a particular rate of climb, right, with a particular rate of climb, what will be the time that is required to the depends upon delta H. Delta H is the difference in the altitudes or say the final climb altitude and the altitude initial climb altitude, or the altitude at which the climb is initiated, the delta H, right, upon rate of climb here R underscore C, So, this, so it returns time here, time for this delta t to climb to that particular altitude. So, this delta t, within this delta t, what is the corresponding horizontal distance travelled? So, that depends upon gamma, right. So, that is x here, which we have discussed. So, x is equals to, again this is a variable because it depends upon gamma, x comma I comma j is equals to V infinity cos gamma, that is V I comma g times cos of gamma times delta t times or t of j comma 1, right. So, when you fix the difference in the altitude, the time required to climb that altitude and the rate of climb, right. So, that means for each and every iteration rate of climb is fixed for the outer loop, right. So, and then del h is already fixed, we want it to be right the altitude. So, it has to climb, should be about 1000 meters, right. So, let me put it down here. So, del underscore h is 1000 meters, h2 minus h1 should be 1000 meters. So, for each and every, because del h is fixed, that is from the mission requirements, and then with different rate of climb you will have different time taken to climb that climb to that particular altitude. So, within this time the horizontal distance covered is V cos gamma times t, the respective t within that time. And say if you want to find out the distance travelled along the flight path. So, say if you want to find out the distance travelled along the flight path within that, so along this direction within that delta t, you have V infinity times. So, that is a velocity of flight, and we assume it is a steady flight condition. So, it is pretty straightforward. So, V infinity times the corresponding time. So, I think there is not much here. So, we can end this. We have almost completed all the required. Yeah. So, we have computed all the required variables here. So, now let us plot here. So, what are we going to plot in the first figure? So, let me subplot. First, our major focus is on what should be the power required here, right. So, power required and as well as thrust required and the velocity also, let us see, and the horizontal distance. Okay, fine, we will plot all these 4 variables here. So, let me take it 4 by 1 by 1, which talks about it is a, so in the figure you will have 4 columns, 4 rows, that is 4 horizontal plots and 1 vertical plot, right. There is only 1 column. If you have 4 by 2, that means you will have 8 different plots. Now, 4 by 1 you have only 4 plots. So, when you say 4 by 2, so in the first row you will have 4 rows, like sorry, in the first column you have 4 rows, in the second column you have 4 rows. So, subplot 4 1 comma 1, this 1 talks about the first plot. You are trying now, you are trying to plot it in the first plot, right. 4 1 comma 2 talks about, like 4 comma 1 comma 2 talks about when you are plotting in the second plot, second subplot of that figure. Okay. What I need to plot is the following. So, I need to plot variation of gamma, is not it. So, gamma, so is any at each and every rate of climb it is one and the same, because the variation is 2 to 20. So, I can plot any one of the column, that should be good enough, all the column variables. So, if I say 1, it stands for a particular rate of climb, right. So, first column when r by when j is 1 here, j is 1, column here represents all the rows here, all the rows and first column. That means gamma matrix, for example, I will show that very soon. Let me just, okay. So, I just commented this. I will run this program and show you how the gamma matrix is. So, climb, enter the altitude at which climb is initiated in meters, right. So, I need to, so let us say from the data, as soon as the aircraft takes off, it has to climb. That is what we have started this program, is not it. So, in the question it is given located, the runway is located at an altitude of 1 kilometer with respect to mean sea level. Okay. So, I need to consider density at that particular altitude for this particular problem, or in general when you talk about solving this in time domain, you can also have density variation with altitude as well, right. So, this particular function returns you that particular value of density at a altitude, which is considered here as the altitude at which the runway is located, that is nothing but the altitude at which climb is also initiated, let us say 1000 meters. So, W should be small letter, I guess, right, is not it. So, here W is in small case. So, now, so when it has executed till this point, that means there are only 2 more lines for it to execute. So, you can assume the code is fine till that point. Okay. So, it is done, right. So, if I take this out here, aspect ratio is 2.8571 that we have talked earlier, 2.86 close to. So, and then CD again, it is varying inside the loop, it is like 70 cross 7, is not it, because there are gammas 10 values of gamma. First let me show you what is gamma here. So, the gamma here, okay. So, gamma here is undog gamma. So, see, there is some issue, okay. Every time I is not getting 0 here, right, I is increasing every time. So, let me just correct that. Okay. So, I will just try to correct it. So, here after I plus 1 again once it comes here, so after 10 it will start 11. So, instead of initializing this I is equals to 0 here, so let me initialize here. So, control V. So, it for inner loop or for outer loop it has no effect, right. Whenever the program completes this inner loop, once it starts for the next variable in the outer loop, once it assigns the next rate of climb. So, this will also make the variable of that inner loop to 0. That way it will help us to find out, have the same columns of like at the same size. Yeah. So, this is 1000 meters. Okay. So, for example, now you can see, so the first column corresponds to when rate of climb is 1, the second column is 2, when third column corresponds to rate of climb 3, fourth column corresponds to rate of climb 4, right, when the rate of climb is 4 meters per second. So, first let us look at gamma here. So, gamma. So, gamma, see here, as I told you, it will be same for all the columns, because we are effectively fixing this variation, is not it, through that for loop command or the syntax that we have assigned in for loop. So, we are actually we have already fixed the initial and the final value as well as step size. So, this is in radians. Now, if you can just multiply this with 180 by pi, you will get to know the degrees, respect to degrees, or say, okay. So, what I can do is gamma times 180 by pi, 180 upon pi. So, this will help me see 2 degrees, 4 degrees, 6 degrees, 8 till 20 with a step size of 2 degrees. So, this is constant and it is same. So, for each and every rate of climb it starts again with 2 degrees, 4 degrees to 20 degrees. So, this yeah. So, the gamma here for I can now plot. So, so now you will be more comfortable to appreciate this. So, considering any one of the gamma, any one of the column in the gamma is good enough for me to plot the variation of any other variable with respect to gamma, right. So, now, so each and every column corresponds to a particular rate of climb, and if you can see here rate of climb is just varying from 1 to 7, right. So, if I just either I can look it from the workspace or I can just write it down here, right. Rate of climb is varying from 1 to 7. So, I wish I may not, okay, I will plot for only one figure. So, you try to plot it for the rest. Okay. So, let me take subplot 4 comma 1 comma 1, okay, gamma, and then what am I plotting it for? You can use either for loop, I am making it explicit here. So, gamma and then rate of so gamma I need to plot for power required, right, power required for climb here, PR, oh, PR for climb, power required for climb, which is colon comma 1, right, the first column, power required, and then I have colon K star. K stands for black color, star stands for the corresponding marker at that particular gamma I comma j comma power required I comma j. So, that particular point is now represented by this marker star. K stands for color code, which is black I am using, and this colon stands for the line type, line type which you can mention explicitly for each and every variable. I would like to use the shortcut here. So, in the same plot I want to plot for the rest of rate of climb as well. So, say plot for gamma 1 comma, because whether you take first column or second column in gamma, it is one and the same. So, I am not varying it. So, I have taken the second variable, and instead of green K, I have taken red here, right. So, the second talks about rate of climb 2, right, is not it? The second value here, or say the second column, it talks about rate of climb when the rate of climb is 2 meters per second. So, I will hold on this plot so that I can superimpose this. So, the third column when rate of climb is 3. So, say instead of I will say green, so hold on. So, I will say instead of yeah, now I am plotting it for rate of climb 4, which corresponds to column 4 here, right, the data here. So, instead of blue, I will take blue and star, and then control V. So, instead of yeah, now I am plotting it for when rate of climb is 5 meters per second, and yeah, M stands for magenta here. Okay, you can so rate of climb 6. So, this will end all the like plots, right. I am no more holding it on this particular, I will say or say after y label and x label. I am just copying it just to save a few seconds. So, power required, that is what we are talking about, power required and CL climb, right. So, this is the power required directly by the system, is not it. So, can we also divide this by or say this is power required by the system. So, what should be the shaft power available? PS for climb performance, PS underscore CL, let us say, for climb should be what, I comma j should be power required for climb upon efficiency of propeller, which is given here, EFF underscore P, right. So, instead of writing PR CL, I will like to use PS CL here, okay. So, and now this is like in watts, yes, of course in watts, power required during climb, CLIMB, right, power required during climb. So, instead of this, okay, you can repeat this for. So, I will just plot any of the two variables, right. So, I will just plot what is the forward velocity as well as, oh, I am sorry. So, I will just plot two subplots. You can repeat this exercise. So, in the second one, instead of PS, what I would like to plot is the velocity, right, what will be the corresponding forward velocity of flight. Okay. So, that sounds help me to identify that it has completed the replacement of that variables from the point where I have selected till the end of the code, right. It will again go to the go to the top of the code and start searching for that variable. So, this is in velocity, which is in forward flight velocity v underscore backslash infinity or inf. What is that? Infinity. What is x label? V infinity. Okay, inf t. Let us see, meters per second. Okay, I am just plotting for this two, and let us see the result. So, here it is not I comma 1, it is I comma j. So, let us run this code again with that. So, the altitude at which we are initiating this climb is 1 kilometer with respect to mean sea level, and we want this to climb to an altitude of 1 kilometer from there. So, you can notice, so infinity backslash infinity stands for v infinity here. So, x label here, gamma in degrees. So, I am plotting here in radians, right. So, let me just correct this, multiply this by, say, if I multiply this by pi by 180, sorry 180 by pi, I will convert this in degrees, right. So, replace 2, 3, 4, 5, 6. Okay. So, done. I will run this again and see, let us hope the proper output. Okay. So, this there is something here, the symbol did not appear, I will just check it. So, the power required during shaft power required during climb is in watts here. So, when it is 2 degrees, so yeah, to have the same what do you call rate of climb. So, for we need to have the label here. So, legend, we can insert legend. Yeah, legend has come. So, the black one corresponds to rate of climb 1. So, red plot corresponds to rate of climb 2, right, and then this is rate of 7th one corresponds to rate of climb 7 at 7 meters per second. Okay. So, here you can notice, no, as the rate of climb increases with a lesser climb angle, you need to because the distance is fixed and the rate of climb is fixed, you need to fly at a very high speed. That is why the overall power requirement during this is about say 1000, no, it is 10,000 watts, which is like 10 kilowatts kind of, right. So, similarly, what will be the corresponding flight velocity is 200 meters per second if you want to achieve rate of climb of 7 with a 2 degrees of climb angle, and it drastically decreases, you can see, when rate of climb is 7. So, it has to be just 20 meters per second, right, the forward velocity, and the power required. So, maybe the scale is quite big, right, here it is 10 power 4 it is approximately. So, you require about 392 watts, right. That means, if you take a 12 cell or a 6 cell battery, what is the power 6 times 3.2, let us say approximately 18 6 3.7 approximately. Each LiPo battery is of approximately 3.7 volts into 6 is like 22 volts, right. So, when you want to supply this much power of say about 392 or 393 is the power upon 22 volts, let us say, you need to supply an amperes of about it takes about 18 amperes, no. So, the motor draws 18 amperes, again you have to divide it by efficiency factor, so that you will get to know what should be the battery capacity. From there, how much time you require, you know what is delta t. So, multiplying that with delta t, you know what is the battery weight required for that particular flight envelope. Okay. So, hope you will extend this program with the other variables as well, like how the drag is varying and then the CL is varying, right, with gamma and for different climb rates here, right. So, okay, thank you, and in the next lecture we will be talking about in the next lecture we will be talking about weight estimation subroutine. So, once we are done with the weight estimation subroutine, we will proceed to find out how to like plan form geometry selection as well as profile selection, wing selection ideally. So, wing design subroutine. Thank you.